Hi again, everybody. Today is August the 12th, and we're going to continue looking at composition of functions, in particular, determining the domains. Before we do that, we have to review how do you find out the domain of a function, just a simple function. And then once we have two functions in a composition, we can use this information to determine its domain. So most of the time that you're dealing with a function, your domain is going to be all real numbers. The domain of most functions is all real numbers. Now we've talked about how to write domain or all real numbers as an interval notation. So this is all real numbers in interval notation. All right, now interval notation is just one type of notation. Okay, another type of notation is called set builder notation. And it looks like this. It starts as the set of all x's such that x is a real number. So we can write it like this. X is a real number. That just means from positive infinity to negative infinity. This type of notation is called set builder. So you may see that being used in some of the Math Excel questions. It's just a different way of expressing a set of numbers. You got interval notation, you got set builder notation. Okay? Set builder notation could also look like this for it. The set of all x's such that x is an element, this weird looking E, of real numbers. That's the symbol for real numbers. And then fancy parenthesis. All of these things mean the same thing. This, three different ways of saying the same thing. All right, the only time you got to worry about the domain being something other than all real numbers, you just have to look at the equation and look for a couple of things that will tell you, hey, the domain might be affected. The first thing is, does the function have a variable in its denominator? The second thing is, does the function have a variable under a even root? So even would be like a square root or fourth root or sixth root. And then the last one is the function is a logarithm and it has a variable as its argument. So this part of a logarithm that I'm circling or highlighting in yellow is called the argument. All right, this second logarithm, this is just a natural log, if you remember. That's when the base of the logarithm is e. Okay, which is around 2.71. So if you have a variable there, it's going to have an effect on the domain. Okay, so what makes something affect the domain? The domain are all the numbers that you're allowed to put into the function. If there's a number that when you put it into the function, you don't get a value, like if you put it in and you did it on your calculator and your calculator said error, that value is not in the domain because it doesn't work in the function. Think of like a soda machine, okay? I can put dollar bills in a soda machine. I can put change in a machine and get a drink. Okay, now if I try to take rocks or pebbles and put it in the soda machine, it doesn't work. All right, so pebbles would not be in the domain of a soda machine. I can't put them in, they don't work. All right, so let's take a look at this first one here. when we look at this, if you notice right off the bat, this does not have a variable in the denominator. It doesn't have a variable under a root, and there's no logarithms. So this is going to have a domain of all real numbers because it doesn't fit any of those restrictive cases. Now, the way that we go through it, if you don't see that right away, is we use this little method called NOP, N-O-P. N stands for negative, O or 0 stands for, the O stands for 0, and P stands for positive. All right? All this means is, can the result of this, after you plug a value in, is the result allowed to be negative? Sure. Okay, down here the results are negative for that function. Okay, can the result of this, after you plug in the x, be 0? Sure, right there. Can the result of this be a positive number? Sure, right there. So there's nothing that this value can't be. And so, therefore, there's no restrictions on it. But the other way is, there's no denominators with a variable, there's no radicals with a variable expression under them, and there's no log with a variable as its argument. Now, when you're writing these on Math Excel, depending on the question, it might say, okay, write it in interval notation. So this would be the solution in interval notation. That's my domain. In set builder notation, we use the fancy brackets. It's the set of all x's such that x is a real number. Fancy bracket at the end. Okay, and that's the other way that you could write the domain of that. Okay, to get the range, well, I can look at the graph, and I can see, well, the range of this is going to go all the way up and all the way down, so I could write my range the same way. It's going to go from negative infinity to positive infinity. So there was no restrictions on this graph. Okay, now we got a rational function. That means a function that's a fraction. Okay, now if you look at it, it's got a variable in the denominator. So as soon as you see that, you're thinking, okay, the domain is not going to be all real numbers. So you ask yourself, well, what could go into that bottom where it would create a problem? Well, remember, you can't have any zeros in the denominator of a function. Okay, this part of the function cannot be 0. If it is, then you're trying to do 1 divided by 0, which is impossible. All right, so the denominator can be a negative, the denominator can be a positive. Now, where students get confused, guys, is sometimes you guys think, can the value of x be negative? Can the value of x be 0? Can the value of x be positive? Don't think about it like that. You want to think, can the result of this, can the result be negative? Sure, you can have negatives in the denominator, so yes. Okay. Can the result of this be 0? No, because it's in a fraction. All right, so this is no, can't be. Can the result of this be a positive number? And the answer is yes. I can have denominators that are positive. So this tells me how to set up the equation to figure out what the domain is. I know that 3x minus 9 is not allowed to equal 0. So I solve that. Add 9 to both sides. Divide both sides by 3. and x cannot equal 3. All right, now how do you write that in interval notation? It can be all numbers except 3. So that means it can be from negative infinity up to 3, but not including 3. Then I'm going to do the union of that and 3 to positive infinity, but because of the parenthesis, 3 is not included. So this is one way of writing that. Okay, another way would be in set builder notation, the set of all x's such that x does not equal 3. That's another way of writing the exact same thing. Right? So that's our domain here. Looking at the graph, I put this into Desmos, okay? And I can see, if you look here, you see there's a vertical asymptote right here. That's the value, that's the vertical line, x equals 3. So you see that line, that nothing on this graph would have an x-coordinate of 3. It's okay, so when you have a variable in the denominator, take that expression, 3x minus 9, set it not equal to 0, and solve it. That value gets kicked out of the domain. So x cannot equal a 3. It can be anything else, just can't be a 3. All right, our range on this, well, if we look at, these would have arrows on it. They're not there because I just screenshot this from Desmos. But we can see that the lowest y value would be negative infinity, and it comes up, gets really close to 0, but doesn't touch it. 0 is this line, the x-axis in this case, is known as a horizontal asymptote. That means the graph isn't going to cross it. And then right here I can see that the y value is very close to 0 and then goes up to infinity. So that's the other branch of my range. Okay, so here again we've got case 2, a variable in the denominator. We have an expression that's got a variable in the denominator. Okay, so I ask myself, can this denominator be negative? Now, the x's can be negative. Can the denominator of a fraction be negative? And the answer is yes, that's okay. Can the denominator of a fraction be 0? And the answer is no. Can the denominator of a fraction be positive? And the answer is yes. So what we're going to do is we're going to say this cannot equal 0. It can be anything else, just can't be 0. So I'm going to solve that for not being not equal to 0. I can factor it. Okay, which two numbers multiply together to be 2 and at the same time add together to be negative 3. And that would be, so as I factor that, the numbers that work are going to be minus 2, minus 1. I multiply those, I get positive 2. And when I add them, I get negative 3. That's not allowed to be 0. Okay, well, what would make that, so if either one of these is 0, we got to kick that out. So I want to know what, that can't be equal to 0, so that means x cannot be a 2. This factor can't be a 0, so that means x is not allowed to be a 1. It can be anything else, can't be a 2 or a 1. Okay, writing this in interval notation, I drew a little picture to make it a little bit easier. So if you look at, here's a number line. I put a circle, an open circle at 1 and an open circle at 2. because those numbers can't be in the domain. So now what I can do is I can write out the intervals that would be okay. So any number from negative infinity up to 1, but not including 1, would be okay. So I could express that as the interval parenthesis negative infinity, comma, 1 parenthesis. Okay, this little piece that is in between 1 and 2, anything in there would be okay. But it can't be the 1 and it can't be 2. So I'm going to say, or any number between 1 and 2, but not including them. That's why I use the parentheses. And then the third part of this interval is this section to the right of 2, but doesn't include 2. So that would be the union of, or 2 to infinity. And this would be my domain for that function. Okay, now the range of this function, okay, we can see in this graph here that this function goes all the way, goes from negative infinity up to, that looks like negative 14. So my range is going to be negative infinity to negative 14, and it touches at 14, so that's going to be a bracket. Or here the x-axis is our horizontal asymptote again. So that's going to be from 0, and then it goes up and up and up to infinity. So I would write or 0 with the parentheses because it's not included to infinity. All right, our next special case is when you have an expression that is under an even root, like a square root or fourth root. So I have this right here. It's an expression, and it's under a root. Well, we know that you cannot take even roots of negative numbers. If you tried to do that on your calculator, you'd get an error message. Okay? You can take roots of the number 0. That works. Your calculator would say 0. And I can take the roots of positive numbers, and I get a value. That works. I just can't take square roots of negative numbers. Those answers are imaginary numbers, not real numbers. So I ask myself, can whatever's under the radical, can it be negative? No. Can't have I can have a negative x, but once I plug it in and do the math here, the result can't be negative. Okay, can the inside of a radical be 0? Sure. Can the inside of a radical be positive? Yes. So now I'm going to write it can't be negative. All right, so the way that you would write that, if this is not allowed to be negative, then it has to be greater than or equal to 0. And that's what you do with the expression when you have a variable under the even root. You take that expression and you set it greater than or equal to 0, and then you solve it. So I add 9 to both sides. I divide by 3, and I get x is greater than or equal to 3. So you can see that this graph, the domain, is greater than or equal to 3. So I would write that in interval notation as, interval notation would be a bracket because 3 is included, because it's allowed to be equal to 3, and then all the numbers greater than 3. In set builder notation, I'd write the set of all x's such that x is greater than or equal to 3. Okay, my domain or my range in this case is from 0 to infinity, because this graph would keep going up, up, and up. So my domain would include 0 because it touches the x-axis up to infinity. And that is my range. If I wrote that in set builder notation, it would be the set of all y's such that y is greater than or equal to 0. Those two things mean the same. So that's what you do with a variable under an even root. There's a restriction on the domain. Okay, so our next one, we have a variable under an even root again, but we've got 2 of them. All right, so each one of these is not allowed to be negative. They can be 0. The result can be positive. The result just can't be negative. So x minus 1 has to be greater than or equal to 0. So x is greater than or equal to 1. Okay. 2 minus x has to be greater than or equal to 0. Now I got to divide by -1. And I get x. Don't forget to switch the inequality because you're dividing or multiplying by a negative. 2. So those are the numbers that are in my domain. So if we think about those, if I draw a number line here, and I put a 1 on it, and a 2, okay, this first part are all numbers that are bigger than 1, and this one is all the numbers that are less than 2. Okay, well, all of the numbers greater than 1 or equal to 1 would be everything to the right of 1. Okay, now all of the numbers less than 2 or equal to would include that and would be all the numbers to the left of 2. So our answer here is, where do these two colors overlap? Well, right in this middle section here. That's the overlapping section. Those are the numbers that are allowed in our domain. So in this case, our domain would be from 1 to 2, and it would include both of those values. So domain is bracket 1 to 2. In set builder notation, it would look like this. Fancy bracket, all the set of all x's such that x is greater than or equal to 1, but less than or equal to 2. And you can see that in the graph here. You can see the range goes, or the domain goes from here to here. All right, our range in this case includes 1 and does not go above, let's see, this is 0.2, 0.4, 0.6, 0.8, 2. So I'm thinking that's 1.4. So our range would include 1 and would include 1.4. Okay. All right, so that's how you deal with variables under a root. Now, if the variable is under an odd root, okay, so there was supposed to be a 3 here, like in this drawing. Okay, that's okay. If it's an odd root, your answer for your domain is automatically all real numbers. Because you're allowed to have negatives. That expression can be negative. When you plug in the numbers and you do it and you get a negative, that's okay because that's an odd root. Okay, this can be a 0 altogether. And then once you do the math, can 3x minus 9 be positive? Yes. So then automatically this would be all real numbers. And then if we're looking at this, our range would be the same thing. From negative infinity to positive infinity. So odd roots aren't a problem. Even roots, you got to watch out for. All right, now this is the double whammy. Okay, you've got a variable under the denominator, in the denominator, and you got a variable that is under a radical. Okay, so what we do is we combine those two things. When a number is under an even root, that expression, okay, this 2 minus x has to be greater than or equal to 0. But since it's under a radical, this result can't be a 0. You can put a 0 in for x, but the result of 2 minus whatever you put in can't be 0. So this part of it tells me that 2 minus x cannot be 0. All right, so when we're looking at this list here, this radical cannot be negative, can't be 0 because it's also in the denominator. So the only thing that 2 minus x is allowed to be is a positive number. So I would express that as 2 minus x is greater than 0. And then when we solve this, subtract 2, divide by negative 1, flip the radical, and I can see that the domain is less than positive 2. Okay, so my domain here would be from negative infinity up to, but not including 2. And you can see that in the drawing here. There's a vertical asymptote at 2. So my domain doesn't go past that. All right. If we were writing this in set builder, it would be fancy bracket, the set of all x's, such that x is less than 2. And then we can see our range here would be from negative infinity to positive infinity. So all we did was combine the last two cases. All right, the last one is the argument of a logarithm. Now, depending on how well you remember logarithms, this might be a little new for you. Okay, all right, so what a logarithm is, guys, it's just an exponent. Okay, so when we have logarithms, let's say I'll make a simple one here. All right, this right here is a fancy way of writing 2 to what power is 8. So what exponent would you put on 2 to turn it into an 8? Well, the answer is 3. So that's what a logarithm is. It's asking you for a missing exponent. Okay? If there is no base, like if it looked like this, log 100. Well, when no base is written, the little base right here is actually a 10. It's just not written. This 100, this is called the argument. Up here, 8 is called the argument. So if I was looking at this and I'm like, okay, log 10 of 100, really that's the same as thinking 10 to what power is 100? The answer to this is 2. All right? If it's a ln, okay, all that means, let's say I had ln, I don't know, 10. ln is the same as a base being e, this little number here being an e. So this is asking e to what exponent would make 10. E is known as the natural base. It's like 2.715, etc. We'll learn more about it later. It's not important right now. Okay, so this helps you understand what the restriction is. All right, and here's how you do it. When you have an argument, okay, so let's say if I had 2 to what exponent, all right, 2 to what exponent can be positive, just like 8. I can take 2 and put an exponent on it and create a positive. Okay? I can't put, there's no exponent that I can put on 2 to make the result equal to 0. This exponent is, it would be impossible to turn this into a 0. There is no exponent that I could put on 2 to turn it into a negative. Even if I have a negative exponent on 2, that doesn't make it negative, it just makes it a reciprocal. If I had 2 to the negative 3, that's not a negative number, that is 1 over 8. It's the reciprocal of 2 to the third. All right, so here's the bottom line without getting too involved with logs, because we're going to study logs more in the future. Okay, what you need to know is that this argument must be greater than 0. It's only allowed to be positive. So x minus 3 must be positive. The result of it can't be 0 because there is no exponent I can put on 2 to turn it into 0. Doesn't exist. Okay? There is no exponent I can put on 2 to turn it into a negative number. It doesn't exist. So that's what you do with logs. With logs, you're going to take the argument and you're going to make it greater than 0. That means it's positive. And now you solve that. So that's just going to be x is greater than 3. And if we look at our graph here, we can see that's the domain. It's all of the x values bigger than 3. So in interval notation, that would be 3 to infinity. In set builder notation, that would be the set of all x's such that x is greater than 3. And that's my domain. Okay, my range on this, I can see, is all real numbers. All right, and finally, the last one. Okay, find the domain. And again, we have the argument, guys. That whatever number is right here is called the argument. So I know the argument must be positive. which means it's got to be greater than 0. So x to the 5th has to be greater than 0. Well, if you did the 5th root to both sides to get x, zero to the 5th is 0, so x has to be bigger than 0, which you can see when you look at the graph. There's my domain. Doesn't include 0. And then my range on this would be from negative infinity to positive infinity. Okay? All right, so to summarize all of these, all right, if you have a variable in the denominator, you're going to set the denominator not equal to 0. Okay, kind of messy writing, sorry. All right. If you have a function, if you have a variable under the radical, then you're going to set whatever this expression is greater or equal to 0. All right? If you have a logarithm that has a variable in the argument, you're going to take whatever the argument is, and you're going to say it has to be greater than 0. No equal sign. And then the last case that we did is when you had both of these. When you had a denominator that was also a radical, and in that case it has to be greater than 0. You set the denominator greater than 0. Okay, folks. So that's probably some new stuff. And then the assignment for this is Math Excel number 6. And that'll be due on Friday. See you next time. Isn't that a beautiful background? Unbelievable. Alrighty.